Alrighty guys, had a bell ring, so I had to take just a second and go teach class. Let's go figure out this derivative, right? 1 over radical 9 minus x squared. So you can do a big quotient rule here, but I think making it a negative half power is probably going to be the best thing for you. So let's go do this, right? Okay, finding our derivative. Let's see. If I call this 9 minus x squared all to the negative half power, I have a chain rule. I've got to take care of that outside function, which is that negative half power first. Dropping down the negative half power, leaving the parentheses of 9 minus x squared, and what happens to that negative half power? It drops by 1. Oh crap, so what happens when it drops by 1? You're already in a negative half, now you're at negative 1.5, so negative 3 halves. Don't freak out, it'll be okay. And then we still need the derivative of the inside function. So what's the derivative of the inside function? Well, the derivative of 9 is just gone, so the derivative of negative x squared, I have a negative 2x. I think we definitely need to make this look better. If we make it look like a fraction, then we can figure out where the derivative equals 0 and where the derivative is undefined. Okay. So let's see. I'm going to take a look and see if I can start cleaning things up even before I make my fraction. I have a negative half and I have a negative 2x. Well, the negative times the negative makes a positive. And the half and the 2 will multiply, cancel out and be a 1. So really, those two multiplied together just give you an x in your numerator. And that negative 3 halves power, I'll bring that to the denominator as a 3 halves power. So 9 minus x squared all to the 3 halves power. Okay. Not the easiest, but at least it's not two separate terms that we have to multiply together. We don't have to add or subtract them together. We don't have to find a common denominator. Okay, let's go figure out where our derivative will equal 0. If we figure out where the derivative equals 0, then we're looking at where the numerator equals 0. That's not so bad. That'll just be x equals 0. So I know that's going to be a critical point. So now we have to figure out where the denominator will equal 0. That makes the derivative be undefined. So I need where 9 minus x squared all to the 3 halves power equals 0. And maybe it's not the easiest thing to have a 3 halves power, but if you think about it, if you want this thing to be 0, you want this to be 0 to the 3 halves power. You're really just trying to get the 9 minus x squared to be 0. So you have 0 to the 3 halves power. Well, where does 9 minus x squared equal 0? If I put that x squared on the other side, I'm going to have x squared equals 9, so I'm looking at 3 and negative 3. Okay, I believe we have 3 critical points. We have a 0, which is what let the derivative equal 0, and we have a 3 and a negative 3. That's what lets the derivative be undefined. So we have 3 critical points to test. So let's go test those 3 critical points. Okay, testing our 3 critical points. We'll put 0 in the function, we'll put 3 in the function, and we'll put negative 3. Oops, that's a negative 3 into the function. Let's try 0 first. If I put 0 in the function, 1 over radical 9 minus 0 squared. Well, that's just 1 over radical 9. And I know you're thinking, oh, is that a positive 3 or a negative 3? But remember, when you square root both sides of an equation, that's when you write plus or minus. If you're just saying, what's the square root of 9, it's fine to call it 3. So that answer is just 1/3. Okay, what about putting 3 in the function? Well, let's go see. 1 over square root of 9 minus 3 squared is 9. Well, what happens here? You're getting a 0 denominator. Okay, that's fine. That's undefined. Didn't work. That's okay. I just know that that's not going to be a maximum or a minimum. That's kind of one of those endpoint type things, right? What about the negative 3? I think the same thing's going to happen, and I'm going to end up with a 0 denominator, which is not going to happen. It's going to be undefined. So I know that that's not going to be a critical point. So I know now the tough part is this thing going to be a maximum or is this thing going to be a minimum? Honestly, we'll kind of talk about that later, but know that you have a maximum or a minimum at that point. All right, let's keep going. And I believe we have one last one. Yeah, yes. Okay, so let's go find our extreme values, and don't freak out on this one because you have a piecewise function. It's actually okay. It's just literally in 2 tiny pieces. It's okay. So we're going to find the extreme values of this piecewise function. So the first part of my piecewise function is 5 minus 2x squared. That's where x is less than or equal to 1. And then where it's greater than 1, then we just have a line of x plus 2. Okay, so you don't have to sketch this, and I'm certainly not going to get a great sketch. That's okay. But I'm going to go sketch it and just sort of see what happens so you have a visual. Maybe it'll make more sense on this first one. So I know something's going to happen at x equals 1. On the left of x equals 1, where it's less than 1, we have a parabola. I notice it's an upside down parabola. I see that the vertex of it's up at 5. So give or take, there's my upside down parabola. And on the right hand side of it, I have x plus 2. So I have a line, it's got a y-intercept of 2, but it keeps on climbing. So give or take, my function is looking this way. I kind of wonder if they are meeting. If you're wondering if they are even meeting and they are continuous, go put that 1 in each function. So 1 plus 2 gives you 3, so that will give you a value of 1, 3. There's a point 1, 3 here. And if you put 1 into this function, we're still going to get a value of 3. So they are meeting at the point 1, 3. This is a continuous function. Guess I didn't draw it very well that it's continuous, but we'll know that it's a continuous function. So we're okay. So if we're trying to figure out critical points, endpoints, things like that, that number 1, that x value of 1, is considered an endpoint. It's where it ends this first function and where it begins the second function. Okay, I know one of them doesn't have an equals with it, but it is considered an endpoint. So I'm going to consider that a critical point and just put that off to the side. I know x equals 1 will be a critical point. Critical point x is 1. There's my endpoints. Now let's look at the derivative. Well, don't freak out too badly. You have 2 equations. Go find the derivative of each one. So what's the derivative of the first one that says 5 minus 2x squared? Well, that derivative is just negative 4x. And what about the derivative of the second one, x plus 2? Well, that derivative is just 1. Okay, so we'll look at each one separately and decide what's going to make the derivative equal 0, what's going to make the derivative undefined. Well, looking at negative 4x, what is going to make the derivative equal 0? 0. What's going to make that derivative undefined? Nothing. So how about the derivative of 1? What makes it equal 0? What makes it undefined? Nothing. So we're only down to 2 critical points. Okay, so it says where does the derivative equal 0? I took both derivatives, and I'm thinking of where each one separately equals 0 and where each one separately is undefined. That's all. You just end up with 2 little small ones. Okay, so we have our critical points of 1 and 0, and now the hardest part, believe it or not. There's technically no endpoints at the very, very ends, but that 1 is considered an endpoint kind of in the middle. We have a 0 and a 1. Now the big question, where do you put the 0? How do you know which function to put the 0 in? Well, because we've got 2 functions, right? Are you going to put the 0 into the parabola one, the top one, or are you going to put the 0 into the line? We have to look at your x domain. Where does 0 fit? Does 0 fit into the 0 is greater than 1, all x is greater than 1, or does 0 fit into less than or equal to 1? since 0 fits in this domain, we're going to put it in this function. So I put 0 into the top function, 5 minus 2 times 0 squared, just getting a 5. Oops. You'd think by now I'd know that, right? Okay, so now we're going to go test 1. Now you got to be careful on this one, right? Because 1 is listed in both places, but 1 is not included here. So I'm putting 1 into the first function because it is in that domain. It includes the 1. So 5 minus 2 times 1 squared. That's 3. All right, so in the life of this graph, we have some maximums and we have some minimums. The 5 is a higher number, so that's going to be a maximum point, and the 3 is a little lower. It's going to be, oops, a minimum point. Okay, and I know that my sketch is not the best, but it's an okay kind of sketch. Take a look and see what you notice. At 0, 5, it says there is some kind of a maximum point. I know I didn't draw it exactly right. And it's not the overall maximum because this graph goes on, but it is some kind of a maximum. And you have this point at 1, 3, and what do you know? It really is some kind of a minimum. It's not the overall minimum, it's not the absolute minimum, but it is a relative one, a local one. So when you get a piecewise function, don't stress over it. Look at where you want them to meet, the x values where you're trying to get them to meet, like 1. That's considered an endpoint. Then take each function separately, find the derivatives, and decide what makes the derivative equal 0, what makes the derivative undefined. And then you have to be careful about where you put those numbers back in. But really that's the only hard part about it. So don't freak out when you see piecewise ones. Most of the time, they're actually less work. Usually they're easier derivatives. Okay, so one very, very last thing, and then we are all done, thank goodness. It says that a function's extrema, their maximums or minimums, they will occur at critical points. I think you've already figured that out, right? In that list of critical points, that's where you get your maximums or minimums. But not every one of those numbers is going to be a maximum or a minimum. I think you've also seen that before where we had maybe 3 or 4 critical points, only one of them was a maximum and one of them was a minimum. Some of them weren't maximums or minimums, but they're still critical points. So for example, just a quick little example here so you can see that you have the graph of y equals x cubed. You know the x cubed graph, that car changing lanes. If you take the derivative, you get 3x squared. Well, where is that derivative undefined? Nowhere. Where does it equal 0? At 0. But you can tell on here at 0, it's not a maximum, it's not a minimum. It is a special point in the life of the graph. It's called a turning point, and we will kind of talk about those later, but it's still an important part of the graph. It's just not a maximum or minimum. So let me say that one more time. When you get your critical points, your maximum and minimum come from that list. Not every one of those is a maximum or minimum, but when they're not, then they're usually called turning points. Something still happens there. Can you kind of see that there's a turning point here? Something happens at that point x equals 0. That's for a little later, but know that you still get maximums and minimums from your list of critical points. All right, I think we've got it all. Hopefully I didn't confuse you too much. You do have Math Excel, so work really hard on your Math Excel. Let me know if you have questions. I don't know how much I'll be on my email, but I'll check every now and then.